today here, let's just get out some paper, some scrap paper here, guys. I'm going to give you guys 2 practice questions on molecular ionic net ionic equations, and just see how we do there. And then we'll go over them, and from there, we will see how you're doing here, kind of thing. But these are the kinds of questions you could expect tomorrow. So like I said, tomorrow we'll have a quick little quiz on 2 questions, molecular ionic net ionic. So I want you guys to write out the molecular equation. Let's get you to do all of them, I guess, for right now. Molecular ionic net ionic. Let's do question number 1 here. Let's see, what did I pick here? Let's do sodium phosphate and barium nitrate. Okay, so give that one a try there. We'll do these one at a time here, so you guys can work on that. Sodium phosphate and barium nitrate, aqueous solutions of both those. And like I said, write out the molecular equation, make sure you balance it, write out the ionic equation, balanced, and then net ionic, and then we'll go over them, see how we do here. Okay? I'll give you guys about 5 minutes here to do that, so you're not going to hear anything for a little bit here. And then when I come back on, we'll go over these questions here. Okay, it looks like we got some ionic stuff done here anyway. I'll start this here. And if you're still working on a little bit there, that's fine. But just for the molecular equation here, sodium phosphate, sodium is a 1 plus, phosphate's a 3 minus, of course. So aqueous, and barium nitrate, aqueous. Okay, double replacement reaction, so metal switch, of course. We get sodium nitrate and barium phosphate. That's a 2 plus and a 3 minus, so swap and drop here, and we get that. Now, once again, as always, it's very, very important to make sure you guys look up the states of these now, because we need to make sure that we get the right aqueous and solid here. Otherwise, that's going to change this entire question. If you look up sodium nitrate, look nitrate across the top, find sodium, it's top row, okay? So that'll be aqueous. Barium phosphate, of course, find phosphate across the top, find barium, that'll be in the bottom row, so that'll be your solid there, okay? And that's very important for these types of questions here. Balancing wise, well, let's see here. We have, starting out here, 3 sodiums. So we're going to need 3 sodiums over there. We got 1 phosphate, we got 2 phosphates there. So fairly quickly here, I'm going to have to probably put a 2 there for the phosphates to balance those out, which means I have 2 and 3 is 6 sodiums. I'm going to put 6 there. I got 1 barium there, I got 3 there, so I'm going to put a 3 here. And 6 nitrates, we're good. Okay, so that should be the right balancing there. All right. Obviously, that's a double replacement reaction. Hopefully, we can do those by now. Ionically, what happens? Well, once again, remember, when it comes to ionic equations, we just need to stay the ions to start with, perhaps. Maybe that's a good place to start. So we got sodium, we got phosphate. Sodium comes as a 1 plus ion, and phosphate is a 3 minus, sodium phosphate, okay? And we'll just leave it like that for the time being here. I'll come back and balance that in a second. Barium we got, so barium ions come in 2 plus, and nitrate 1 minus, all right? Once again, on the other side here, we got 6, well, we have 6, sodium nitrates. So sodium, 1 plus, nitrate, 1 minus, and of course, barium phosphate, solid, stays together. So we just rewrite that exactly like you see it now, barium phosphate, like so, okay? So that's exactly what you need to have for that part there, and we got to go back and balance all the ions now as well. So this is where you really need to pay attention to the top part here, okay? We have to think about things like how many sodiums do we have here? Well, there's a 2 out in front and there's a 3 there, that's 6 sodiums. How many phosphates do we have? Well, remember the 2 goes to this and that, so 2 phosphates, okay? Remember, when you're done that part, just of the ionic compound, we have a 6 plus, right? 6 plus. We have a 2 and 3 minus, so that's 6 minus there. 6 plus, 6 minus, 0. Ionic compounds are neutral when you put them together, okay? Over here, we got 3 bariums, so 3 bariums. We got 6 nitrates, 6 nitrates, okay? On this side here, we have 6 sodiums and 6 nitrates, 6 and 6. And of course, there's just a 1 there for the barium phosphate, and we have barium phosphate there. And of course, it's stuck together because it's the solid, okay? You should now, you don't have to, but I will underline the spectator ions, the ones that appear both the same on both sides. In double replacement, you have to have 2 spectator ions, double 2, so sodium and nitrate. Notice I have exactly 6 and 6, and I have 6 and 6 there as well. So those would be called your spectator ions, okay? We're going to take those out of the equation, and all you have to do now is write what's left over, and that would be your net ionic equation. And so your net ionic equation, therefore, would be, I'm going to write the barium one first here, so 3 barium 2 pluses, and 2 phosphates, gives you barium phosphate. Like so, and you're done, okay? 3 bariums, 3 bariums, 2 phosphates, 2 phosphates, combined together give you that solid. Good? Yeah? Okay. They really honestly don't get a lot tougher than that. So if we can do that one, we're probably going to be, I would assume, probably okay. All right? So that would be an example of a double replacement that I would give you tomorrow. Yes? Okay. So, questions, anyone? Okay. Let's look at single replacement here. Single replacement, let's see here. Oh, let's give you a little copper. And let's say, iron 3 chlorate. Okay. Once again, I'll give you a little time to get that done there. And when you're done that, we'll go over that one there. Okay. So copper and iron 3 chlorate. Once again, the copper is going to be a solid chunk of copper, and the iron 3 chlorate would be an aqueous solution, of course. It has to be. Okay. So I'll let you guys work on that for a few minutes here, and then when I come back on, we'll do that as well. Alrighty, let's see here. So, molecular equation, copper and iron 3 chlorate, okay, aqueous. Metals switch places, of course. We're going to get iron by itself and copper 2 chlorate. And remember, it has to form the most common charge, so we have to make sure we look at the charges for those. Copper 2, copper 1. Copper 2 comes first on the periodic table, so we need to use that one there. Okay. We need to balance it, of course. So let's see here. We need 3 chlorates on this side, 2 on the right side there. So let's put a 2 here and a 3 there, and a 2 here and a 3 there, and that should be good. All right. Next, we need to write out the ionic equation. There is no charge on the copper, okay, because it's not part of an ionic compound. Okay, we get charges from ionic compounds in water. This is not an ionic compound. This is just a metal by itself. There's no charge on this, so I don't want to see any charges there. We have Fe3 plus here, iron 3 charge because it's part of an ionic compound, metal, non-metal, and chlorate. And I think this time here, what I'll do is I'll just balance it right now here. Iron 3 plus, we got 2 irons, so 2, and 6 chlorates. Okay. Once again, do the charges balance out? We got 2 times 3 plus, so that's 6 plus, and a 6 minus. Looks good. Okay. 2 Fe solids. Once again, don't forget, no charge, not part of an ionic compound, just a metal by itself. Okay. And then we get our copper 2 plus here, and our chlorate here. Okay. So 3 coppers, 3 copper 2 pluses, and of course, once again, 3 and 2 is 6 chlorates there. In single replacement reactions, you'll get 1 spectator ion, single 1. So that is the only thing that's exactly the same on both sides, the 6 chlorates. We take those out, and we just write what we wrote before. So this is the easy part here. Net ionic, 3 copper solids, 2 Fe3 pluses, aqueous, gives me 2 Fe solids and 3 copper 2 plus aqueous. Okay, and we're done. All right. Those are 2 pretty straightforward types of questions that you would get tomorrow, for example, for single and double replacement, molecular ionic, net ionic. Okay. All right. Good. All right. And if you have any questions about that, obviously feel free to ask tomorrow before class there, kind of thing, or you can ask me really quickly tomorrow before we do. I gave you a list of I gave you 6 questions on this, of course, and if you need any more practice, just look at those again, just double check them, and if you're not sure about anything tomorrow before we have our little quiz here, just ask. Okay. I'm going to hand out lesson 7 right now, so let's we're going to move on here today, lesson 7. Good thing you're here. 5. Let's see. Yeah, please do. Okay. Everyone's got one? Yeah? Okay. So, all right, so lesson 7. Here we go here. We're going to talk a little bit about limiting reactants today. Limiting reactants basically implies that one of the reactants is, well, has a kind of a limitation to it. A chemical reaction can only proceed, okay, if we have both reactants available to us. So if those 2 reactants can come together, combine together, we can get products. But if I run out of one of the reactants, then I can't make any more products because that reaction would stop. So that's what we're going to talk about today. The reactant that runs out first is known as what we call the limiting reactant. Okay? And it determines, so that limiting reactant determines the maximum amount, there's that word, of the reaction that can take place. Okay? And when we think about amount, we think about N, of course. All right? So the other reactant or reactants, so sometimes there's going to be sometimes there's 3 reactants in a formation reaction, for example. The other ones are what we would call excess, all right? And another thing that I will use for excess, by the way, when I label the limiting reactant here today, I'm going to use an LR for limiting reactant. And when we talk about excess, I usually put excess, okay, for that one there. Now, we usually only label the limiting reactant, but just so you know, if you do see the excess, that's what it means, all right? So let's take a look at a few problems here. That's the best thing that we can do for us here. This says, during a formation reaction, a student reacts 20 grams of magnesium and 75 grams of sulfur. The only product that you get is magnesium sulfide. So let's take a look at this. The only product we get here is magnesium sulfide. Magnesium's a 2+, sulfide's a 2-. We swap, drop, and reduce, don't forget. So that's a solid, of course, ionic compound. To make magnesium sulfide, I'm going to need some magnesium and some sulfur. Okay. We want to balance it, of course. So I'm going to, in order to do that, I'm going to have 8 sulfurs there, 8 there, and 8 there then. Okay. So I'm going to balance it. I'm going to do like I did all the other days, of course, and I'm going to line up the important stuff underneath each one. It says here I have 20 grams of magnesium, 20 grams, and I also have 75 grams of sulfur. Okay. Now these 3 questions here, they're going to ask you what's the limiting reactant, what's the mass of the magnesium sulfide form. Perhaps they might ask what the mass of the excess reactants left over. It doesn't matter. These questions are all done the same. I don't care what the questions are. If there's A, B, C, like today, for example, on your homework, it says, what's the limiting reactant? How much product would you expect to get? Something else it'll ask you. It's the same 3 questions. All you have to worry about is this, guys. You're going to do them all the same, okay? Yes, in this particular question, usually with limiting reactant questions, we're trying to find out how much product can we make from this, okay? So we're going to ask you for this here. At some point in time, more than likely, that's what you're going to be asked to find. Okay? There is a few other questions we can address with these types of questions, but most of the time it's going to be that. Okay? So we do these exactly like every other question. We say, okay, well, let's figure out the molar mass, which is 24.31 grams per mole. Remember, not the number out in front. And the molar mass here is 256.56. grams per mole. Okay? So, we're going to get the molar mass for both of those, of course. Something that we would have done last day anyway. Now, here's the thing with these questions. Remember, we wrote out a balanced chemical equation. And the balanced chemical equation tells me that if I took 8 moles of this and reacted with 1 mole of this, I would get 8 moles of product. Correct? That's what the balanced chemical reaction tells me, right? The question is this. Do I have this ratio, 8 to 1, based on these masses here? Okay? And honestly, I can't tell you right now because I don't know. Because remember, we can't compare masses. We can never compare the mass. But we definitely could compare N. Okay? So let's find N for both of these. And once again, I'll just reiterate this again. This is an 8 to 1 ratio. And that would give me 8 moles here perfectly. The question today is, do we have an 8 to 1 ratio there? And I'm going to tell you, I'll give you the answer. We don't. Okay? But let's find out what actually we do have down here. So let's find the moles for both of these. If I take 20 divided by 24.31 here, I get 0.88 or 0.8227-ish. Okay? And if I take 75 divided by 256.56, I get 0.292. Okay? Et cetera, et cetera. Now, if, in fact, we did have an 8 to 1 ratio here, that's what we're supposed to have, an 8 to 1 ratio. Do we have that here to here? Is that an 8 to 1 ratio? What do you think? No? Okay. Most of us can probably look at that and say, no, we don't have an 8-to-1 ratio. Okay? If it was an 8-to-1 ratio, if this was 0.8 here, I'd have to have about 0.1 here, yeah? In other words, 0.8 moles here, roughly, would react about with 0.1 moles there, correct? 8-to-1, yes? So actually, by looking at this question, I can quickly tell you that this here, do I have 0.1 moles here? No, I have more than 0.1 moles, yes? So actually, right now, I could probably tell you that this is the excess, and that this would be what we call my limiting reactant. Now, I'm going to give you another way to find that out, because it's not always that obvious. I will tell you, what I tell you right now, it works for every question that we do, okay? So if you just want to always do this, that's fine, because the next one we're going to look at is going to be a little bit more complicated, okay? So you might be able to look at this one and say, hey, this should be a 0.8 to 0.1 ratio, but I have 0.29, so I know I have more of that stuff than I need. So that's my excess. The other one has to be my limiting reactant. Okay? The other way to do this, and like I said, would encourage, is this. If you want to get them down so you can compare them, the easiest way to compare these elements or reactants here is on a 1-to-1 scale. So if I take this here, okay, this is for 8 here. What I'm going to do is I'm going to divide my moles by 8, okay, because there's an 8 out in front. When I divide it by 8, it brings it down to a 1, okay? This is already for 1 right here, so I don't have to divide there by 1. If there was a different number there, I would divide it by a different number, whatever, okay? And we'll look at that on the next one here, okay? But I'm going to divide the first one by 8, and it's going to bring it down to a 1. So when I divide 0.8227, okay, when I divide that by 8, I get about 0.1028 moles here. Okay? So what I'm going to do is I'm going to compare this one for 1 mole, and this one is already for 1 mole. I'm going to compare these two numbers. The smaller of the two numbers is the one that runs out first. Okay? Because remember, 0.1028 moles technically should react with 0.1028 here, yes? Or if I had 0.292 there, I need 0.292 here. Basically what I'm trying to tell you is that out of these two, one of these reactants is going to run out first, yes? They're not in a perfect 8-to-1 relationship. They are, well, it's more like a 0.8 to 0.3 kind of thing, almost, all right? So one of these is going to run out first. Here's the thing. When this one, so we're going to label this is my limiting reactant here. I'm going to put a little LR up there, and I'm going to circle it so that you know that that's the one that's going to run out first. Why are we doing this? Because remember, this right here tells me how much product I can make. Because when I run out of magnesium, can I make magnesium sulfide? No. Pretty tough without magnesium, right? So once you run out of the limiting reactant, the reaction will stop, okay? It's like when you go to the lab and you decide, hey, I'm going to take the bottle of this, and I'm going to take a bottle of this, and I'm going to dump it into each of the solutions, and I'm going to mix them together and see what happens. That's basically what's going on here, okay? Well, at some point, one of those two, I didn't measure anything out. I didn't get a perfect 8-to-1 ratio. I just mixed two things together. One of those two is going to run out before the other one does, unless you get incredibly lucky. And you'd have to be really lucky, okay, to get that perfect ratio if you didn't weigh anything out. So there's basically a like 1 in like a billion chance kind of thing. But anyway, you would, like I said, once you run out of that, you can't make any more product. So the thing here is, why do we do this? Because we need to find out which one the limiting reactant is so that we can determine how much product we can make. Okay? The limiting reactant always determines the amount of product you make. Because once that runs out, reaction stops. Okay? So we need to get N over to here just like last day. So basically what I'm going to tell you right now is you know what, this sulfur doesn't matter right now anymore, okay? Did it matter at the beginning? Yes, because I need to figure out which one's going to run out first. Does it matter now? No, because I have lots of that. There's going to be stuff stuck around after. We'll talk about that later. But over here, this right here tells me that how much I can make over there. Now, here's the only thing you have to remember. Remember, this right here, this number, 0.1028, is only for 1 mole, right? Because I divided it by 8, correct? So if I'm going to move this number over to here, I need to multiply it back by 8 to get back up to there, right? So that's an option for you. You might say, well, could I take this number here, this 0.8227, and move that over to there? And the answer is sure you can. And that actually was for 8, that 0.8227, I should say. So I can move that right over to here as well. But remember, you can't round these numbers until the very end. So there is a chance you might have to go back and do the calculation again. All right? So let's take a look here. Do I have that number? Yeah, I got this number here on my calculator still. So I'm going to take this one, times it by 8, and I get 0.822706701 with the molar mass of magnesium sulfide, which is, let's see, 24.31 and 32.07, so 56.38 grams per mole. And we're going to multiply those two numbers, and that's how much product I can make from this reaction. Okay, let's see here. So times it by 0.822706705.1, and I get 46. Well, I got to leave it at 46 grams, guys, because I only have 2 significant digits in this question. Okay, the 20 and the 75 are only 2, so I have to leave it at that. All right. Is that okay so far? Okay. Now, there is other questions that go with this as well. They can get a little bit confusing, but if you think about it, there's a couple ways you can do them as well. I guess we should probably mention it today here. Real quick here. How much, another question could be, okay, so what happens in this question? 20 grams of magnesium is all used up, okay? It gets entirely used up, it's gone. Well, it changes form into magnesium sulfide, I should say, okay? That's all gone. 75 grams I had of sulfur here. I didn't use it all, okay? So if you actually did this reaction, you would actually end up with 2 things. You'd end up with some leftover sulfur and some magnesium sulfide, okay? Because all the sulfur does not react because it's in excess quantity, okay? How much sulfur actually did react? Well, there's a couple ways to figure that out. First one is, okay, probably the easiest here, is when you have this on a, and by the way, the other question that goes with this is how much sulfur reacted, how much sulfur didn't react. You can pick either one of those to do, and you can get the other answer by simply subtracting at the end. Okay, and I'll show you what I mean here. So it doesn't really matter. But look, if this is an 8-to-1 ratio, this is a 1-to-1 right here. So this 1 should react with 1 right here. Okay? So 0.1028 moles here of magnesium should react with 0.1028 moles of sulfur. I had 0.292 moles here. So how much reacted? Well, 0.1028 on a 1-to-1 scale, guys. 0.1028 should react with 0.1028 moles here. Okay? If you disagree, well, remember this number is actually the same as this one. So if you want me to say it a little differently, 0.8227 moles here would react with 0.1028 moles here, correct? Okay? So if I know that 0.1028 moles reacted with this 0.8227, well, 0.1028 times 256.56, the molar mass of sulfur, if you multiply those two together, okay, and once again, you want to use the unrounded number, so just keep that in mind. you're going to get, yes, 26 grams would have reacted. Okay. Now, there is a little thing about this as well. So 26 grams would have reacted. And actually, if you look at this one, sometimes, not all the time, okay, so you can't do this all the time, but in this particular example, and once again, I caution you, it doesn't work for all of them, but in this particular example, look, 20 grams and 26 grams gives you up there 46 grams, right? So the 20 and the 26 gave you the 46 there. That is not always the case. It really depends on a few factors, okay? But that's how you would figure out how many grams reacted. You could say how many grams didn't react. Well, that's pretty simple actually now. That we don't need any complicated stuff. If I had 75 grams and 26 reacted, 75 minus 26 is 49 grams. That doesn't make sense, but unreacted or didn't react, okay? That's what's left over basically, okay? All right. Now, I'm not going to ask any of those questions today about reacted or unreacted or didn't react or anything like that, but that's kind of some of the stuff that probably should know anyway, okay? At least I don't think I asked you that today. Maybe there's one question that I ask you, all right? Let's look at one more example here real quick. This one here is a little bit tougher just because there's more stuff here. So let's take a look at this here. Formation of aluminum hydrogen sulfide. Formation aluminum hydrogen sulfide. Hydrogen sulfide is a polyatomic ion. It is in the top left. It's not a very common one. We haven't done it for probably quite some time here. Aluminum hydrogen sulfide. Aluminum is a 3+, hydrogen sulfide is a 1-. So we'll do that there. Okay. Aluminum hydrogen sulfide. Actually, I haven't done that one for a while. Let me just double check here. Where is it? Yeah, hydrogen sulfide. Yeah. Okay. So 3+, HS is a 1-, so swap and drop. To make that, of course, formation, each element by itself, aluminum, right, hydrogen, and some sulfur. Okay. Obviously, we need to balance it, so we need to make sure. So let's see here. Once again, as always, sulfur is going to be the tricky part, right? Sulfur is 3 on that side. We've got 8 on this side. Lowest common multiple of 3 and 8, 24. So let's put a 3 there and an 8 there. And then we got 8 aluminums. And how many hydrogens? We've got 24 hydrogens on that side, so I'm going to put a 12 here. Okay. Now we have an 8-12-3 ratio here, and that's going to give me 8 moles of product here. So once again, we have to decide, you know, these numbers that they've given us for masses, is it going to be an 8-12-3 ratio? And I can pretty much guarantee you when you get these types of questions that they're not. Okay. So 5 grams of hydrogen. I'll put that here, of course. We got 75 grams of aluminum. Put that here. And we have 100 grams of sulfur. Okay. And once again, we need to figure out the moles here. We need to compare moles to moles to moles. So molar mass of aluminum is 26.98 grams per mole. Molar mass of hydrogen, of course, 2 of them, so 2.02 grams per mole. And the molar mass of sulfur, 256.56 grams per mole. And we're going to have to go through and figure out these moles for each one here. Now, like I said, before it was an 8-to-1, and most of you guys could see that relationship, 8-to-1. Is it 8-to-1? No, it's not. We got more of this stuff, etc., etc. This is a little tougher. This is 8-12-3. So, like I said before, always just divide by the number out front when you get the moles, and let's compare it on a 1-to-1-to-1 scale, and then figure out which one is the least, and that's your limiting reactant. It works all the time, guaranteed. Okay. So the reason I'm telling you that right now, because after I do 75 divided by 26.98, I get here 2.779. Right away, I'm going to divide that by 8 because it's still in my calculator. Okay. And the reason I'm dividing by 8 because there's an 8 out front here, and I want to get it down to 1 so I can compare them all. Okay, so this is 0.347. Okay, let's do the next one. 5 divided by 2.02, and I get here 2.475 divided by 12 in this case because there's a 12 out front, and I get 0.206. Okay. And last one here, 100 divided by 256.56, I get 0.389. And I'm going to divide that one by 3, of course, because there's a 3 out front, and divided by 3, and I get 0.1299. Okay? Now, this is, once again, what you've done is now you're saying, hey, if I reacted a mole of each one of these, this was a 1-to-1-to-1 ratio, which one of those 3 is going to run out first? Okay? And the answer is, of course, which one runs out? If we're going to be doing a 1-to-1-to-1 ratio, which one do I have the least of? The answer is sulfur, right? Sulfur has the least number of moles, so this is the one that's going to run out first. So I'm going to put my limiting reactant up there, so I know, okay, and I want you to do that as well so I can tell which one you're picking. Remember, once I run out of sulfur, I no longer can make aluminum hydrogen sulfide. It stops. I can maybe do aluminum and hydrogen, but there's no more aluminum hydrogen sulfide. So this limiting reactant tells me how much product, the amount of product I can make, right? Well, let's see. This is for 1 right here. Don't forget. That's for 1. I need to get to 8 here. So times it by 8 for that one there. That number's still in my calculator, so that's a good thing. So I'm just going to go times 8, and I get 1.03 here, 939 moles, with the molar mass, and I could figure out the mass of product formed. Okay? Yeah? Good? Okay. Does someone have the molar mass of aluminum hydrogen sulfide by chance? Anyone? Yes? No? No? Oh. All right. What do we got here? 3 sulfurs, 3 hydrogens, and 1 aluminum. 126.22? Does that sound right? I think so. I said 22. Ballet. Let's times that by 1.03, 9392994, and all said and done, I get 131.1921 grams here. And one last thing about this, as far as significant digits go, okay, well, how many significant digits can I have? And the answer is, well, you look in the question and you see some different stuff here. You see 3, I see 4, I see 4. I guess the question is, what's determining the amount of product that you can make? And the answer is, well, it's the sulfur that really determines how much product I'm making, right? Now, the sulfur has 4 significant digits right there. Let me do that in a different color. 4 significant digits, right? So in my answer, I could have 4 significant digits, okay? Because that one is accurate to 4 significant digits, I could have 4 in my answer. So let's write down 131.2 grams in this case, okay? Most of the time when you get the questions, they're all going to have the same number of significant digits. So you don't really have to worry about that too much, but if there is different ones there, you go with the limiting reactant one, okay? Because remember, it all comes down to limiting reactant. And the answer is, what are these two here? Well, yes, this does turn out to be excess, and so does this. It doesn't really matter anymore because, remember, the limiting reactant determines how much product you can make. Can we figure out how many of the other ones reacted? Sure we can. If 0.1299 reacted here, then I guess we should have had that here and here as well, okay? So we should have had that here and here, and we could figure that out based on molar masses. We could figure out the mass of each one that we would have, okay? Is that okay? Any questions? Anyone? I'm going to tell you right now, that's pretty much as hard as these get. Okay. What you have to keep in mind is, okay, first of all, balanced chemical equation, super duper important. Okay. After you get all the moles, divide them by the numbers out in front that you see here. So in this case, 8 and the 12 and the 3. Okay. That gets it down to a 1-to-1-to-1 ratio, or a 1-to-1 or whatever. Or if you had 4 reactants, it would get it down to a 1-1-1-1 reaction. You take the lowest one, you move it over, and that'll tell you how much product you get. Do you get any other questions from this kind of thing? And the answer is no. Because if I'm giving you all the reactants, there's nothing else to find for the reactants, right? What else are you going to find? Well, I gave you the mass of all of them. Other than, of course, you know, possibly which one's excess, how much is excess, how much actually reacted, sure. But almost, well, 99.9% of the time, you're asked to find how much product you can make from this, okay? And that's what you're going to have. Now, tomorrow, I don't know if we'll get there tomorrow, but we're going to do limiting reactants with solution stoichiometry and gas stoichiometry as well, and those are the 2 lessons we have left, and, well, one more with the titration, which is really solution stoichiometry. But it's basically all the same stuff now. This, now that I've shown you this, the rest of the stuff you could probably do actually over the Christmas holidays if you wanted to. You could do C equals N over V. You guys know how to do P equals nRT. So you could find N from those things, compare them if you had to, move it over, and figure out how much product you get. That's all we're going to do. Okay? So it's all the same stuff now. This is the only other thing that's kind of holding you back, other than, you know, a couple examples here or there. All right? So, any questions on limiting reactants? All right. I will tell you this. Let's flip to your last page here for your actual questions here, guys. When you get to these questions here, you do have to take note that not all of these are they're not all limiting reactant questions where you're gonna have to do all the work. The thing is if you notice the worksheet we did yesterday, okay, which by the way, I guess if there's any questions, we can do that here shortly. But look at the very first one. I'll help you. I'm going to just talk about this one for a second. It says, number 1, during the combustion reaction, 75 grams of butane, that's butane by the way, combustion reaction, right? So combustion reaction. 75 grams of butane is allowed to react with an excess amount of oxygen. Is this a limiting reactant question? And the answer is yes and no. Okay? What we've been doing so far is limiting reactant questions. Okay? We have been. Look up here for a second, guys. Just look, watch. It says this with excess oxygen. Well, if this is excess, by default, that has to be limiting reactant, right? Did they tell you a mass of oxygen here that you needed to use? The answer is no, they don't. They don't have to because it's excess. Don't care, right? I got lots of it. So the point is, we tell you this mass here, and you can move stuff over. So this question is something that you would have done yesterday, right? If you look at the questions from yesterday, you notice the word excess. How many times did you see the word excess yesterday? Lots, right? Lead 2 nitrate is reacted with excess potassium bromide, was the question yesterday. Why are they telling you that? Because they're telling you that the excess one doesn't have anything to do with this question. We need to focus on the lead 2 nitrate, right? We need to focus on this here. They're telling you for you which one the limiting reactant is and the excess by telling you that, okay? So you're going to get a few of these questions here where it's just basically straight stoichiometry. The next question, they're going to tell you this plus this gives you this and this or whatever kind of thing. And they're going to tell you as soon as you find out that you have a mass here and a mass there, or basically how do you know you have to compare the two? It's this simple. If they tell you information about this and they tell you information about this, my question to you is which one runs out first? Okay? Then you have to do the comparison like we did today's lesson. If they don't tell you information about two things, if they only tell you information about this here, then this doesn't matter because it's excess. They're telling you that that's excess. Okay? Do you understand? Okay? So you will get both of these questions today. You will get some that look like the top one here, and you'll get some that look like the bottom one. It's important to understand, you know, what do I really need to do there, right? And remember, we're talking about, and then there's a question also that does looks like this, kind of thing like that. Listen, it's called limiting reactants, not limiting products, reactants. So if they only give you one reactant, well, that's your limiting reactant because there's no other thing, there's nothing else there. So if they give you information here, well, then that's all you can do, right? It's not really limiting reactant because there's only one piece of information there. That's all there is, okay? So you're just going to use that to figure out other stuff. That's fine, okay? The only time you actually have to do the comparison, like I said, was if you have information here and here, okay? And then you got to decide what you're looking for over there, okay? Good? Questions, anyone? All right. Okay, question number 3 from yesterday's homework, if you need to pay attention here, was, let's see here. It was zinc, I think, and chromium 3 chloride, is that right? Zinc and chromium 3 chloride? Let's see here. Yeah. So this is from homework yesterday, number 3. It says here that a sample of zinc and chromium 3 chloride, aqueous, gives you chromium and, let's see here, zinc chloride, of course. 2 plus, 1 minus. Balancing, you're going to have to put a 2 there, 2 there, 3 there, 3 there. It says you started with 50 grams. 38.5 are left over. So really, you only used 11.5 is what you used, okay? By the way, it says, and then it asks you what mass of this did they use? What mass of the chromium 3 chloride solution was used? So of course, we're going to have to find the molar mass and N for that as well, of course. And that's what they want to know. This is actually a limiting reactant question from yesterday. The thing is which one's the limiting reactant? Well, I'll tell you. Look, you started with 50 grams here. 38.5 is left over. So we didn't use all the zinc. The zinc didn't get all used up. So this is my limiting reactant here. This is my excess, right? So really that's what that question is, but I wasn't able to ask you that yesterday because I could ask you that because I told you which one the limiting reactant was, right? You didn't have to find it. So in this case here, we'd use the molar mass, 65.41. We'd find N. Let's see here. 65.41. 0.1758. We'd move N over to here because we need to find the mass of the chromium 3 chloride. So we're going to move it over there. To do that, it's a 3:2 ratio. So divide by 3 times it by 2. Oh. Divide by 3 times by 2. We get 0.117-ish. And we also need to take chromium 3 chloride. So 3 chlorides, let's see here. That's 35.45. Oops. 3 times 35.45 and a chromium, which is 52. So 158.35. And multiplying those two together, we get 5 for me, but I think I didn't use the rounded. I rounded my number. I think it's 18.6 is the answer, if I'm not mistaken. I think. Yeah. So if you use the unrounded number, you get that, 18.6. Okay? For that one there. Any other questions from that sheet? Yeah. Number 2. 2, let's see, where are we here? Yeah, silver nitrate and silver nitrate. It's number 2 from homework yesterday. Silver nitrate and excess sodium chromate. Sodium chromate. Is chromate a 1, 2 minus? Yeah? Yeah. So, sodium chromate, aqueous. Of course, you'll get sodium nitrate and silver chromate. And let's see, 2 there, I guess. You'll have to look those up. Now, chromate's not on there, like I told you guys yesterday. Chromate's not on there, but look up the the sodium nitrate. This is aqueous. This is going to be your solid here by default, basically. Especially if they're talking about a precipitate, which I believe they do. Yeah, and they're producing 2.89 grams of precipitate. There. Actually, I should probably balance this before I go any further, eh? Let's put a 2 there and a 2 there. That's probably good. They want to know what mass of silver nitrate was present. So what mass here? So find the molar mass, find N. Find the molar mass, find N. When you find N here, you got to move it over to there, times it by 2, of course, because it's a 1 to 2, right? So times it by 2, molar mass should give you the mass. Should be okay. Okay? Once again, this, they tell you in the question here, by the way, that they say it reacts with excess sodium chromate. So basically what they're saying, that's the excess. By default, this is your limiting reactant here. Okay? So what they're saying is this depended on that right there. Okay? So those two are directly linked. If they actually didn't say that, then you might say, well, I could figure this out, but how do I know it's not this that's making that? Right? So that's why they say it in those questions. And they don't necessarily always say it, but that's what they're trying to get at with this limiting reactant excess stuff. Okay? Yep. Any other questions, guys, from that? We're good? All right. All right, so you got those questions there. We'll go over those tomorrow. Don't forget, quiz tomorrow, molecular ionic, net ionic equations. So please be ready for that. And I should be back tomorrow, so yeah. Hopefully, better be.